Now entering the boardroom is the team from Purdue University. They will try to convince Mr. Trump that their idea for sustainable 3D printer ink is worth investing in. Ultimately, Mr. Trump will have to decide if this team and their idea will be hired or fired.
Morning, Mr. Trump. My name is Callie Frost.
I'm Jesse Ham.
I'm Shruti Dasika.
I'm Tinky Wang.
We are here to talk to you about an exciting new opportunity to invest in environmentally friendly ink for the 3D printer industry. As we will discuss later, we believe there is huge market potential. It's technically feasible, environmentally friendly, and there is opportunity to implement this business model in many locations across the globe. So we would like to begin by summarizing our proposed product, describing the problem it is solving, and then we will tell you why we think it is both economically and technically feasible.
Everyone is listening to you now.
In short, we want to use food waste as a feedstock for a PLA composite in 3D printer filament.
Ay.
Okay, I know it sounds complicated, but let's break down the plan step by step. I would like to begin by summarizing our business model. Step 1, divert waste shellfish for use as a filler in polylactic acid, which is a commonly used degradable bioplastic. Here we use the term shellfish to describe molluscan species such as oysters, mussels, and clams. The global production of molluscan shellfish is 23% of the total world aquaculture production. Of this amount, the inedible shell is approximately 90% by weight of the shellfish, which results in almost 14 million metric tons of waste shells per year, which currently may go to landfills or be used for other purposes. Now you may be wondering why we chose shellfish as our waste stream. Well, we utilized a weighted decision matrix to compare several possible waste streams such as hazelnut shells, cocoa, and spent coffee grains. Among other reasons, shellfish won out because of the abundance of the waste stream in locations where PLA is also produced. Which brings me to the next step in the process, which is the use of ground shellfish in the form of calcium carbonate in polylactic acid. Lactic acid, which is made from fermenting corn or other materials, is polymerized into polylactic acid and made into resin pellets. The PLA resin is combined with the calcium carbonate and a composite is born. The composite is now extruded at a specific diameter and wound onto coils. This leads us to step 3 in the process. The filament can now be sold into the 3D printing market where individuals or businesses can print objects with this new biodegradable PLA composite printer ink. Mr. Trump, you might be asking yourself, so what problem are we solving? Why should you or anybody else care about this? I would now like to walk you through the current paradigm of shell waste management. In the shellfish production cycle, shellfish meat is first separated from the shell, then shells are either recycled or discarded as waste. In developing countries, this may end up manifesting as illegal dumping or open storage of shells. For example, in South Korea, up to 40% of shell waste is dumped in coastal areas. So by diverting this waste for another purpose, we can reduce environmental impacts from dumping. As you can see, recycled shell material is used in various applications, including animal feed supplements and for environmental remediation. However, we feel that utilizing this product for biopolymer filler results in a high-value use of the waste stream. Due to the ample amount of this waste, we feel that demand for this waste stream for all of these purposes will not outstrip supply. Next, I would like to discuss the end of life of 3D printed items in order to highlight the environmental trade-offs between current products on the market and our proposed product. There are 2 major polymers that dominate the plastics 3D printing market. Acrylonitrile butadiene styrene, or ABS, which is a petroleum-based plastic, PLA, or polylactic acid, and the newly emerging PLA plus biofillers. So after a 3D item is printed, it is often sent to a landfill. ABS and PLA will both degrade slowly in landfills. However, biofillers may somewhat speed up this process. Recycling is another end-of-life scenario. ABS is capable of being recycled in our current system. However, this is not currently practical for PLA or a PLA plus biofiller. Industrial composting of PLA is very promising, and adding biofillers has been demonstrated to speed up the composting process. And the final fate is leakage to the environment, which is an all too common fate in developing economies. In this scenario, the PLA plus biofiller would be the fastest to break down in the environment and wouldn't leave behind harmful residues. So Mr. Trump, You may be asking yourself, how's this really going to work?
That's right.
Shruti will give you a technical analysis of PLA properties and describe the feasibility of our plan to use shellfish waste as a filler in PLA.
The choice of printer filament material that is to be used to obtain a 3D printed product really depends on what the user wants to print. The key decision criteria for choosing the right kind of material are the ease of printing. How easy is it to print the product on the basis of feeding the filament into the printer, the printing speed, flow ink, flow accuracy, and the number of fill attempts. Visual quality. Is the finished object visually appealing? Maximum stress. When the object is stretched, how much stress the object can take before breaking? Elongation at break. When the object is stretched, by how much the length of the object is increased before breaking. Impact resistance. Under sudden impacts, with what amount of impact energy does the object break? Heat resistance. How much heat the object can sustain before softening and deforming. Layer adhesion. How good is the adhesion between the layers of material? Because better the layer adhesion, the more isotropic the object will be. The main polymers that exist in the market today are PLA, ABS, PET, nylon, TPU, and PC. These snapshot profiles of the polymers in their pure form help in making a quick decision while picking the most suitable polymer for 3D printing application. It can be seen in the case of PLA that it has the highest ease of printing, provides good visual quality, and exhibits relatively high maximum stress, thus making the material quite strong and rigid. Additionally, unlike other polymers here, PLA is biosourced, biodegradable, odorless, and has good resistance to UV. However, it has low ratings for elongation at break and impact resistance, making it brittle. So a study was conducted in Japan which closely demonstrates the technical feasibility of our idea. So first, the PLA composites were dissolved in methylene chloride. The CaCO3 veterite used was obtained from the carbonation process. The two were mixed for 5 hours continuously and fully dried for 8 hours at room temperature. The mixture was subsequently hot pressed uniaxially under a pressure of 40 megapascals at 180 degrees Celsius. So what they have found from the experiment that about 30% of the shellfish waste as a filler improves the mechanical properties of the PLA filament. It improved the modulus of elasticity from 2.5 to about 3.5 to 6 gigapascals. There was no brittlity observed in this composite, and there is a high bending strength achieved.
So you may be wondering, how are you going to make money on this idea?
Many millions of dollars.
That's what we thought. Well, Tianchi is going to talk you through the economic feasibility of this plan.
Hello, Mr. Trump. 3D printing market is expected to reach $21 billion by 2020 and $30 billion by 2022. The United States will be the major driver for the growth of the market. Prototyping, product development, and innovation are the three most common reasons companies are pursuing 3D printing. Siemens predicts that 3D printing will become 50% cheaper and up to 400% faster in the next 5 years. Also, the future will bring the democratization of manufacturing, which means everyone can become the manufacturer of goods. According to the process and technique we apply, the business model we propose requires additional facilities of 1 dryer, 2 mixing heater, and 1 miller. Based on the market price, the estimated cost of them is $25,000. The capital cost will be about $1 million by purchasing them at one time, or $225,000 per year if we pay off them in 5 years. Based on the critical process of producing PLA shell composite, Mr. Trump, you can produce 582 metric tons of this composite per year. Because we can save money by producing the PLA shell composite, there will be a payback period of 5.6 years to cover the initial capital costs. In fact, PLA composite filament has a higher value than pure PLA filament. If we pay for the capital cost in 5 years, the annual additional cost will bring you extra revenue of $8.73 million per year. Also, compared to using calcium carbonate as filler, using shells will save you $21,000 per year, which is $37 per metric ton of filament produced. Although there are some uncertainties of cost, basically you will make millions of dollars every year.
Look at those numbers.
However, as with any great idea, there are certain challenges to overcome.
Oh, that's not good.
So Jesse is going to talk us through the domestic challenges and opportunities and the possibility of expanding this model to the global market.
In the United States, there are over 55 million pounds of shellfish produced. So the only minor roadblock that we'll run into is that most aquaculture takes place along the coast with a huge presence in Washington state. This creates a logistics barrier when considering the other component we need for our product, PLA, that's almost exclusively produced in a NatureWorks facility in Blair, Nebraska, almost as far away from the coast as possible. But this facility puts out 150,000 tons a year and is currently accounting for about half the global market. But this shouldn't stop us. The demand for PLA is going up and up and up, so new facilities will need to be built. The reason PLA is currently produced in the middle of nowhere is because it is heavily dependent on corn as a sugar source, but new methods of production are knocking on the door. Studies have shown that wastewater streams from fisheries and aquaculture can be used as a sugar source to produce a higher quality of PLA. But guess what? This isn't just a US thing. The aquaculture waste stream is all over the world and far more abundant in other countries. China consumes over 40% of the world's shellfish market and has been projected to have the largest growth of PLA production in the next few years. This would be a great opportunity to create a symbiotic relationship between aquaculture and polymer production. So in conclusion, our product is environmentally friendly because it's biodegradable and a fossil fuel alternative. It's a better product because the PLA composite provides superior printing filaments. And finally, and most importantly, our product leads to a higher profit and huge potential for economic growth. So Mr. Trump, what do you think of our proposal?
Thank you very much. That's really nice. Thank you.
What do you think about our group?
Tremendous talent.
We did. So we want to know, are we hired or fired?
You're hired.